Uh, Hello. Uh, so there was a homework due nowish, and there will be a quiz on Wednesday. The quiz is going to be on electromagnetic waves, focusing on uh, intensity and the Poynting vector. 3, 4, and 5. All right. We can look at problems 3, 4, and 5. Uh, Also, important announcement, Thanksgiving is coming. So uh, our homework won't be due in a week. Homework will be due in 2 weeks because we've got a week off. Uh, so I guess we can start looking at those problems on the homework. There it is. Right. Yeah, I can go through them. So homework problem 3 gives the electromagnetic field, and it asks for everything else that you can find from it. Field is only in the z direction. And it is 1000 volts per meter at its peak amplitude. Ten inverse meters.
In progress.
So we can start getting our directions off the bat. So the cosine function tells us that if x gets bigger and you want to keep the phase the same, then t needs to get smaller in order to keep whatever is inside of here the same. So that means that as t increases, I'm sorry, if x gets bigger, t also needs to get bigger, because there's a minus sign. So if t increases and x increases, if you have them increasing at the same rate, then the part that would have been a peak will still be a peak. So if you have something that looks like this, later in time, it'll just have moved in the X direction. So it's traveling in the X direction. The speed that it's traveling will just be the speed of light because it's in a vacuum. So too many. For the, sorry, I'm just pulling up too many things at once. For our speed, we have that our frequency times our wavelength must be the speed of light. So the frequency is going to be speed of light divided by the wavelength. And we don't quite have the wavelength. We have the wave number. So wave number relates to wavelength a lot like angular frequency relates to period. Our wave number is 2 pi divided by our wavelength. Is 2 pi. Or 20 pi meters. So this works out to be 4.77 times 10 to the 8 hertz. For the direction of propagation, x. And the equation for the B field, well, there are two pieces to that. One of them is getting its geometry, what its direction will be and what direction it'll be traveling. And the other one is finding its magnitude. So for the direction it's traveling, it needs to travel the same way as the electric field does. So it's going to be in the x direction. It's going to have the same wavelength, same wave number, same angular frequency. For the magnitude, we can get that from electric field is equal to the speed of light times our magnetic field. Magnetic field then will be 3.3 times 10 to the minus 6 Tesla, because we've got our electric field magnitude right there. And for the direction, the wave travels in the E cross B direction. So x equals our electric field direction, which is z, across our magnetic field direction. So z cross y gives minus x, so we need minus y. So putting it all together, and then it's going to have the same cosine term. And its angular frequency needs to be 3 times 10 to the 9 radians per second. And it needs to have units of Teslas. So that one just had a lot of pieces in it. And if you have your equations of the electric field, it's just how do I get from there to what I need? So the direction of travel comes from our pointing vector in this cross product. And we find it out from there, traveling in the x direction. And the relative magnitude of the magnetic fields comes from electric field equals speed of light times magnetic field. For number 4, it is looking at what kind of electric field strength would give you an energy density of 1 joule per cubic meter. So our energy density from our electric field is 1/2 epsilon naught E squared. But we have just as much energy in our magnetic field. So our peak energy density, or energy density at any given point, is epsilon naught E squared. Because E equals 1/2 epsilon naught times our electric field squared. And we've got the energy of the magnetic field adding to that, which is just as much. So this is our energy density at any given point. Our average is just going to be half that. Or Emax, or the amplitude of the electric field can be used there. So we need to divide both sides by epsilon naught, multiply both sides by 2, and then take the square root. And this gives 4.75 times 10 to the fifth volts per meter. And our intensity, 1/2 epsilon naught times the speed of light times e squared. And then we can just plug in because we have all of these values now. It works out to be 3 times 10 to the 8th watts per meter squared. So that 1 joule that each cubic meter has travels 3 times 10 to the 8th meters. So it takes each second. So you could get a prism, which is 1 meter by 1 meter by 3 times 10 to the 8th meters, all putting their energy through that 1 square meter patch. So that would be the intensity of all the energy in that volume passes through the patch. So we just have that 1 cubic meter would have 1 joule. So 3 times 10 to the 8th cubic meters will have 3 times 10 to the 8th joules. And number 5. So 5 is the most.
Can I ask a question about that one?
Oh yeah, go ahead.
So I did this in a totally different way, but I
Cool.
managed to get the same answers. So I started by I thought the energy density was actually like a pressure because you have energy per volume. And so I set pressure equal to 1 joule per meter cubed and then went from there. And I actually got the same answers.
Bizarre.
I can send you a picture of it, or it's in the homework that I submitted, but
yeah, cool.
it's basically the formula was pressure equals intensity over speed of light, right? And then that works out to be the same.
So you
So
used
1 times
energy density as a pressure? Huh.
Yeah.
So energy density would be joules over meters cubed, and pressure is newtons over meters squared. So the joule is just a Newton meter, so dimensionally it works out. Huh, cool.
I don't know. I just thought that was interesting.
Yeah. All right, neat. So yeah, the 5th one, the most open-ended, and the answer, I think, somewhat surprising, is yes. So we've been learning about how electromagnetic waves are changing electric and magnetic fields in a region of space with no charges and no currents. But Maxwell's equations allow for stable and unchanging magnetic fields or electric fields to be in some region of space. So the Gauss's law and Gauss's law for magnetism says you can't have fields that go like this for either electric or magnetic fields if there are no charges. It can't just all spread out in all directions because if it's spreading out, then there's more going out than going in, and Gauss's law says no. Same with more going in than going out. Our loop ones say you can't have fields that make a path like this in our region because there's some curl, and that's going to require either a current or a changing field of the other type. So that doesn't work. But you could have a really, really boring field that does this. So a field like this, if you put, a box around any volume of it, as many arrows point in as point out. So Gauss's law or Gauss's law for magnetism, totally fine. And not making any loops, so you don't require any change in field. So if you had an electric field that just pointed up with a uniform strength everywhere, that's totally fine. So for instance, between two charged capacitor plates that are holding a constant amount of charge, you could see an electric field that looks like this. And those plates couldn't be part of the region with no charges, but the space between them has no charge in it. So yeah, it's allowed. You could have a current carrying wire and you've got your magnetic field that goes around it. So if you included the wire, that wouldn't be allowed, but you could look at this region over here, and that would have a stable magnetic field through it if the current wasn't changing. So yes, it is allowed by Maxwell's laws. I guess for our first example of something like that is you just have a charge. Electric field goes away from it. And you just look at a region over here. There's an electric field. So yeah, it can be done. Any other ideas on number 5 for unchanging fields?
So like electromagnetic waves are just light, right? So if there was no electromagnetic waves, then you wouldn't be able to see things that didn't have charge, right? Like, right?
Correct.
Then
If
there'd
there
be no
were no
light.
electromagnetic waves, you wouldn't be able to see things, period.
Right. So like, I mean, that's just what I was thinking, it's like if something is not charged and has no current flowing through it, then there's still electromagnetic waves on it, right? That are hitting it, so you can see it.
If it's in the light, but that would require, so a region that has light in it does not have unchanging electric and magnetic fields. You need to look real small scale to see those changes, but a
So
lit
it would be like
room,
if you're in like a black box or something, or what?
yeah. And a black box, if it is at all warm, will glow with infrared light, right? So if you really wanted this to occur, you'd need a 0 Kelvin black box.
And then the argument is that you would still be able to see a non-charged thing. Or there'd be electromagnetic waves around it, but maybe you wouldn't be able to see it.
So if it was 0 Kelvin and it wasn't charged, no, you wouldn't be able to see it because it'd be dark in there. If you shined a light on it, it could bounce off, but then you've put energy into the system. So to properly have a situation where there's unchanging electric and magnetic fields, then yeah, technically you would need to be dark. If you're counting the scale of a light wave as having electric and magnetic fields, which if you want to be technically right, you should. Most people don't go that level of detail, but technically There are. Yeah, but we can't even make 0 Kelvin black boxes. So getting absolutely no electromagnetic fields is uh, tricky. You can get less and less by getting things colder and colder and farther away from light. But actually getting to 0 is a problem. Yeah. That was just kind of a grapple with the big ideas question. Cool. New stuff for today. The biggest thing is going to be Snell's law. Before we get into that, I would like to just do a little practice with what we had last time. Norman Way. So there is a radio telescope. So big disc. For us, it's going to work like a mirror. Uh, so the math for sound, if we're just doing ray optics, it'll still work for sound. So if we've got a 20-meter focal length, and we are 2 meters above that. So someone is just trying to shout off of this big old bowl for reflecting radio waves, and instead it's going to be reflecting the sound of their voice. So where would those sound waves focus, which would give us our loudest echo? Or to write it a different way, di over d. Uh, it's just plug it in, 1 over 20 meters, 1 over where it's going to, sound will collect and then spread out from again, plus 1 over 2 meters. So it would be 220 meters away from the bottom of the reflecting pole. So if something comes in near the focus point, it's going to be not too different from coming in from the focus point. So if rays or waves from the focus point hit our reflecting mirror, they would leave parallel. So we're leaving from near there, so they're not going to leave parallel, but they're going to leave pretty close to parallel. So they're going to need to travel a very, very long distance before they focus into their echo. Good with this? All right. Let's try this one. Why would we not need to take the speed and the sound into account? Well, the simple and unsatisfying answer is it doesn't appear in any of the equations. The better answer is it's not changing anywhere in the problem. So if we're traveling faster in one area and slower in another, then Snell's law could be applied to sound, which we're going to learn about today. But even if you were doing this with just light, if this entire problem happened underwater and light was traveling slower, nothing would change. So there's no bending due to it traveling slower if it's always at the same speed. One way of looking at where this focusing happens is at the point where you get the shortest transit time, or occasionally a maximized transit time, but an extremum of your transit time. So whether you're going fast or slow, I need to give myself more space. Whether you're going fast or slow, if you've got that there, our focal point there, things are meeting up there. These paths are the same distance. Because one path makes you go a little farther out to the side, but the mirror curves upwards a little bit. So those actually work out to be the same distance. And if there's the same distance and it's always traveling at the same speed, then it's going to take the same amount of time to get there. And then if it takes the same amount of time, then all the waves will arrive in phase. So that's why it works out to meeting at that point. That's a different picture of it, not the ray optics point of it. But if we just look at the ray point of view, if you slow down the ray, it doesn't bend it, as long as you're not slowing it as it moves from some process somewhere else. Yeah, light and sound Same focal point, same answer. For this one, we've got a radius of curvature of 20 centimeters. And that means that our focal point is going to be at 10 centimeters in. So getting the signs right is particularly tricky on this, which might have caused your concave convex problems. So for a mirror, it counts as a positive focal length and a positive radius of curvature if it's on the side that the light comes from. So this would have a focal distance of negative 10 centimeters because it's on the wrong side, or no, the other side. It's not on the side where the light is coming from. So if we've got our object at 15, so we just do what the rays would do. If something is going to hit the center of the mirror, go out just like it came in. If something is going to go towards the center of curvature, then it's going to bounce straight out in the direction it came in. And if something is going to be going towards the focus, if something is coming towards our focus, it needs to go out parallel. So these aren't meeting anywhere, but if we trace them backwards, we can get a pretty good idea where they're meeting. So doing it mathematically instead of using our pretty rays. So our image distance is going to be 1 over minus 10 centimeters plus 1 over minus 15 centimeters. And should be minus 6. So the negative sign is indicating that it is on the other side of the mirror. So it is going to be upright, and 6 is going to look like it's inside the object. So for the magnification equation, negative our image distance over our object distance. So it will be 0.2 times as tall as it used to be. So if it used to be 1 centimeter tall, it will now be 2 millimeters tall. So you are correct that we are getting, oh wait, no, we are, we're getting things smaller, which is typical for our convex mirror. If you hold a spoon fat side out and look at yourself, you look not very big. Right. Uh, so the tricky part with these is just going for positive and negative. Let's get to Snell's law. So light can reflect if it's hitting something shiny. It can be absorbed if it's hitting something which is dark. It can pass through, but when light passes from one medium into another medium, it can bend. So if you've got some light, and it goes from somewhere to somewhere else, say water to air, or glass to water, or a prism to the water that the prism was submerged in. The index of the two materials may not be the same. And if it's not the same, if it comes in at any angle other than straight in, it's going to bend. And Snell's law gives a pretty easy mathematical treatment for what the new angle will be. So the sine of the angle times the index before it transitioned into the new material is equal to the sine of the angle times the index after it transitions. So there are a lot of ways of looking at this. You can use your electromagnetic wave equations. I want to go back to thinking about constructive interference. So you will end up having the light add up with itself and not canceling itself out to nothing if it is in phase with the paths that are almost exactly the same to it. So this is one way of looking at why light travels in a straight line in normal circumstances. Because the straightest path is the shortest. And if you vary from it just a little tiny bit, you add distance, but very, very little. So it still is close enough to in phase. Whereas if you compare this path and this path, the amount of distance between the two is actually pretty large. So one way of looking at how light travels is it doesn't take the shortest path. It takes the least time path, getting from one place to another place. So one way of thinking of light is it's like a good lifeguard. So let's put light itself aside for a moment. And we've got a good lifeguard. And a bad swimmer. So the lifeguard wants to get to the swimmer quickly. So there are many, many paths that the lifeguard could take. They could do this. That's a bad lifeguard. So that's an option. So you could just travel straight there. You could, because you're really fast on land, just take a short path on land. And when you get to the water, swim the rest of the way. Yeah, so I'm not intending to do that explicitly, but that's very much our big idea. The path where the derivative of your total time with respect to your starting angle is 0 is going to be where you minimize. And that's going to be the path that the light takes or the best lifeguard takes. So yeah, that's very much the big idea. So let's look at our paths. So path A has the perk of having the smallest amount of time in the water because you take the shortest path to the water. So our lifeguard, they can run faster than they can swim, but they're still a pretty good swimmer. Path C has the least total distance, path D, and path B. So if you were trying to get there in the least possible time, how would you get to the swimmer the soonest? Right. No one picks C or D, which is quite good. So if you were an absolutely terrible swimmer, uh, and you went a billion times faster on land than you did in the pool, path A would be your best choice. But if you're not that extreme, path B would be the choice to take. If you could swim just as fast as you could run, path C would be your best choice. And if our lifeguard was a penguin, they might take path D, where they're just going to be faster if they can swim more and spend less time on land. But I can go with path B. And if we use our optics equation for it, I like penguins. We can look at this angle. This will be our theta 1. This will be our theta 2. So in the medium where we're traveling faster, that's going to have the low index, which means the sine of the angle is going to be bigger. And in the medium where we're traveling slower, it's going to have the high index. So that means the sine of the angle or the angle needs to be smaller. So this is our qualitative how to optimize, and Snell's law is if you put numbers on it and get it all to work out, that gets you there the fastest. And that is the path that light will take. Quick demo thing for it. Let's do a new screen share.
I do have a question about that actually.
Yeah, go for it.
So in that setup, you know how far you should go on the beach because you know how far the distance to the swimmer is, right? Or like how far in the water the swimmer is.
Mhm.
Right? So like light doesn't know how far it needs to travel, does it?
Oh, wow. Yeah, that is a. So one way of looking at it is the wave takes all possible paths, spreading out, and the paths that don't work out just destructurally interfere and aren't observed. And the paths that do work out to be shortest paths get constructive interference or enough that you actually can observe them. But it does seem like the light, I'm giving foreknowledge to the light, which you're absolutely right, shouldn't have. So it's kind of impressive that it doesn't quite sit well with you because I'm giving the light information, decision-making power that it shouldn't be able to optimize anything. It's just a wave. But the paths that aren't shortest possible paths are going to just have destructive interference, make them not happen.
Okay, yeah, that makes sense.
Cool. Yeah, it's a really good question / observation. So light. So this is showing our red laser pointer going from air into water. It is worth noting that not all of the light makes it into the water. So if you have a flat surface between two different media, some of it goes through and some of it bounces off. Usually the closer you get to a glancing angle, the more bounces. And the more straight in you go, the less bounces. Something you can see is that for just bouncing off the surface, the law of reflection holds. Angle in equals angle out. But once it goes into the water, the angle that it approaches with is different than the angle it goes away from the surface at. So because it travels faster in the air, that means low index. So low index comes with high angle, and high index comes with small angle or small sine of the angle. If you want to look at it as a wave, a different way of seeing why this has to happen is the waves need to remain in phase with each other. So it's going to slow down when it enters the water. So in order for everything to still line up, if it travels a little farther in the air, then it'll go farther sideways. And for it to stay in phase, it needs to bend inwards. So something really cool to look at is if we flip this around. We get to a bigger angle, bigger angle, bigger angle. And eventually, it can't get out at all. So that is a very real thing that happens. Light can get trapped in high index materials. So if we've got water for our higher index and air for our lower index, so if our N1 will be 1.33 for water and 1 for air, well, the sine of our first angle theoretically could be 0.9, right? There is some angle that will give us a sine of 0.9. The maximum value of our sine will be 1. If we come in at just about 90 degrees, so 0.9. So if we came in at the angle that will give us a sine of 0.9, what do we get for the sine of theta? Needs to be more than 1. So if you are making this, trying to solve this equation, and you end up needing a sine of an angle which is bigger than 1, it just can't do that. So if it can't bend into the other medium, it doesn't. So this consequence of Snell's law is total internal reflection. So if you would need some nonsensical result of Snell's law in order for the light to exit, it just doesn't exit and instead bounces on the surface of the water, staying in its original medium. And the equation for what will force this to happen is going to be the sine of the other angle is going to peak at 1. So that's going to be the biggest angle that we can get on the top, and thus the biggest angle we can get on the bottom. So n1 times the sine of the critical angle. So the critical angle is just the transition between some of the light being able to escape from material and all of it being trapped. So that's going to happen when we are at exactly 1 for the sine of the angle as it escapes, because it can't bend more than 90 degrees and still pass into the air. So this is the equation for our critical angle. So this is sometimes used to make particularly shiny gems. If you cut them in such a way that light from the top can't make it out the bottom, but instead reflects on the facets at the bottom of the gem back up to the top, more of the light comes out the top. Also, if you have an optical fiber, which is just a tiny little fiber that light can carry through, we've got our fiber. And light is traveling inside this fiber. If it hits the edge of it, it can't leave unless it hits at a wide, unless it hits close to normal. So instead, it just gets trapped in the optical fiber. So you can carry light through a tiny little fiber as long as it doesn't hit at a sharp angle. This is all these hits at glancing angles, it's stuck inside. It's like a pipe for light. Right. Let's do a little Snell's law practice. So polarized sunglasses while fishing. We'll get to the physics of polarization. There's more there. We will do that physics. That'll take a little. So Snell's law. And our goal is theta 2 for the angle it's going to be traveling in the water. So isolating for theta 2. So we've got the sine of 35 degrees divided by 1.33 is going to be the sine of our angle. So we just need to take the arc sine of that. And it works out to be about 25.55 degrees. So for these, you can work in radians, you can work in degrees, but just make sure you know which one you're working in, and then you'll be fine. Questions on our Snell's law problem?
So on a homework, should we put 25.5 degrees, or would we need to put 25.5 plus like 270, or how would it go?
Oh, fair enough. I will usually just ask for things from normal. So I guess if I wanted to answer this more completely, I would say 25.5 degrees from normal.
Okay, sounds good.
And that, yeah, that'd be the easiest way of expressing things. It's just, if you need to be clear, just say you're measuring from normal. We don't need to get fancy. Well, I guess in one of these problems, I will get fancy. We're not there yet. So total internal reflection, wouldn't happen here, because it happens if something is trying to escape the higher medium material. So I have the power to change this into something that makes sense. So if we're going from the higher medium to lower medium, then it can get trapped and fail to escape the high medium material. So what is the widest angle that you could escape this material at, / the smallest angle that you can't escape that material at? That's what our critical angle is. Yep, 58 degrees is correct. So the sine of the angle is going to be n2 over n1. So our angle is going to be the inverse sine of 1.4, 1.65.
Professor,
Mhm.
how do we go about labeling which one's going to be N1 and 2? Is it just which one we're given first?
Oh, so I suppose as long as you're consistent, you'll be okay. But I think it makes the material you start in do N1, the material you go to do N2.
All right.
The equation's symmetric, so if you don't follow that, you'll still get the right answers. But going from 1 to 2 just makes sense to me. Seems like a logical progression. Oh, the critical angle one isn't symmetric because it already assumes.
Yeah, that's what I was
Yeah,
thinking.
but the original Snell's law, if you work from there,
Okay,
then it doesn't actually matter. But yeah, for the critical one, you're traveling from 1 to 2. Yeah, I made the assumption that you're traveling from 1 to 2 and deriving that formula. But Snell's law, you could go from 2 to 1 if you wanted to. Apparent depth later. All right. So how much light bends is just the difference between its original angle and its final angle. Just yeah, our n1 will be 1 and our n2 will be 1.01. See if you can get our bending. So this is just doing Snell's law twice. The process isn't particularly interesting, but the result, I think, is. So that is our formula. So we're just dividing the sine of our first angle by 1.01, and we take our inverse sine. So if we start at 1 degree from normal, we end up at 0.99 degrees from normal. So that is a bend. One of these days, I'm going to draw a satisfying V. 0.01 degrees. Not much. So we're getting somewhere around 700 times as much bending if we start at 89 degrees than if we start at 1 degree. So the fact that the indices are so close to each other helps make this particularly noticeable. But yeah, if you small angles, it doesn't usually change much, and you get much more dramatic changes in angle the closer you get to tangent to the surface and the farther you get from normal. So to take this to a slightly bigger extreme, that gives us the physics of a mirage. So if we have air and hot air, so realistically, you don't get a air is here and then hot air is here and there's an absolute sudden transition. Really, you'd have cooler air and then warmer air and then hot air and then very hot air, something a little more even. But if you have, say, the surface of a road on a sunny day, right above that surface, it's going to be hotter. And if the air is hotter, that causes the air to take up a little more space, become a little bit less dense. So both of them are indexes of refraction close to 1. But remember, air doesn't have an index of quite 1. So the cool air is going to have an index which is slightly higher. So there's still going to be some bending as you transition from cool air to hot air. Or another way of looking at it is you're still going to have some critical angle where the light doesn't transition from cool air to hot air. And it bounces off the surface. So this is the shimmery surface that you might seem to see if you look just barely above the surface of a dark road on a very sunny day, or the surface of a sunny desert, where it seems to reflect like the surface of a pond. And that's just at glancing enough angles, even small changes in your index of your index of refraction matter. Whereas if you just looked straight down at the surface of the road on a sunny day, you'd see the road. So I mean, you could be looking down and see what's over here. And it's going to be shimmery instead of a nice smooth reflection because the temperatures aren't perfectly even, the densities aren't perfectly even. It doesn't make the cleanest of reflections. Another cool consequence of refraction is that depths appear shorter than they really are if you're looking from air into water or from any low index material into a higher index material. It will look less thick than it actually is. So if you look at something, got ground, you've got something on the ground. Our water has a finite depth. And someone looking into the water is going to have the light bend closer to normal as it enters. This is an exaggerated amount of bending. Too much exaggeration, in fact. But it bends closer to normal. If they had a different eye over here, so it would seem like the object they're looking at is over here. You just continue the straight lines from where it seems like they're looking, but really it's deeper than that. The actual effect of this, how much less deep it seems, depends on the initial angle. For apparent depth calculations, it's almost always assumed that the initial angles are very close to normal. So if our initial angles are close to normal, then some assumptions work that wouldn't otherwise work. So our horizontal distance traveled by the light is x. Our actual vertical distance traveled by the light would be our depth. And how far it seems like it traveled, I'll call d prime. So if the angles are close to normal, then a handy assumption can be made about the angles. This is just Snell's law, but with one plugged in for air. And if the angles are small enough, we can make the theta is approximately equal to sine of theta small angle approximation. So this works in radians. but the sine of 0.01 radians is very close to 0.01. So if we make that assumption, oops, this needs to be a 1. And it also holds, if we're making this small angle approximation, that the cosine is going to be very, very close to 1. So then our angle is also approximately equal to the tangent of that angle. So our theta 1 is going to be, a tangent of theta 1 is going to be our opposite, which is x, over our adjacent d prime. And our same assumption can be used for theta 2, except its opposite is still x, but its adjacent is d. So then if we're trying to figure out what the ratio of the depths is going to be, it is the index of refraction. So for water, it should be 1.33 times as deep as it looks. Or to put it another way, it looks about 3/4 as deep as it actually is. So these assumptions are great for small angles and junky for big angles. So this apparent depth really only works if you're looking pretty much straight down into something. So if you're standing in something that's not water, and your legs look kind of short now, they seem like they look like that. Legs didn't actually get shorter, they just look shorter when you're standing in this fluid. What is, oh wait, that was a silly word. What is the index? The apparent depth was 0.7 meters. We already knew that. So if it's got an apparent depth of 0.7 meters, what would its index be? So this would be a material with an index of index of refraction of, yes, 1.43, which I don't know why you're standing in it. It's probably a bad choice. Our last idea for the day, already something we talked about a bit, is dispersion. So the idea for dispersion is just different frequencies have different indexes of refraction. So it usually works that if you have your wavelength and your index, over the visible range, most materials are going to have higher indexes for the shorter wavelengths than they do for the longer ones. Uh, so the prism, the rainbow, that's this working out. If the opposite pattern holds, where as you get to higher wavelengths, you get higher indexes, that is anomalous dispersion. So it's not a law that always when your wavelength increases, the index of refraction decreases. It's just usually that I guess violet would be at the other end instead of blue. Usually, as you move to the longer wavelengths, there's less bending. for the visible range, usually. So instead of having wavelength is equal to speed divided by frequency, you would have wavelength at a given index is our speed divided by our frequency, or the speed of light divided by n times the frequency. Or it's wavelength in a vacuum divided by n. So there's usually more bending of the violet end of the rainbow than the red one. All right. So next time, going to look at how light will refract through a curved surface. And that's going to be our launching point to see how lenses will work. So we're going to move into chapter 33 for next time. I'll post a homework probably today or tomorrow, but you'll have almost 2 weeks to do it. Any last questions for the day?
Yeah, I had
No.
a question real quick. In the lab that we turn in tomorrow, is that supposed to have a phasor diagram like drawn on it?
You don't need, if you have one, cool. If you don't have one, that's fine. I think of the guiding you through the steps is to help you understand it. You don't need to include it. If you did, that's cool. If you didn't, that's okay too.
Okay, thank you.
Sure. Anything else? All right, then I'll see you on Wednesday or in lab or when I see you.
All right,
Sounds good. We'll see you tomorrow, Professor. Have a good one.
see you,
All right.
Professor.